This week we are going to do, the plan is to do another two problems with charges in an electric field, in a uniform electric field, to see how they appear in the exams, because they always combine them with other topics. I mean, the electric fields with energy considerations, or with kinematics, or with something else. So let us see now this problem. A particle of mass m and charge q is in a uniform electric field of strength E. The particle has acceleration A due to the field. Okay, they represent the acceleration with this A. It should be this. Anyway, doesn't matter. Show that Q over M equals to A over E. All right. How do we start? We start with what we know about the electric field. What is the definition of the electric field? Is that the field is the field E is, by definition, is force per unit charge. Force per unit charge. If they ever ask the definition of the electric field, which they do quite often, they want you to express this definition as force per positive unit charge. Anyway, so in general, this is the definition of the electric field for any for any configuration of charges. And okay, what else do we know? We have acceleration involved here, so acceleration and force, net force. Obviously, it reminds us of Newton's second law, isn't it? So what is Newton's second law? The force, according to Newton's second law, is mass times acceleration. And already here we have all the ingredients of this expression that we need to end up with. So let us start here. For example, here in this expression of the electric field, we can replace the force with m times a. So what do we have there? We have E equals to m times a divided by q, and already we're getting closer. So we just need to rearrange this a bit. We can divide this field with a, so that we have this ratio even if it's upside down. So from there, if we divide by a, the acceleration, what do we have left? We have m over q, and then we can reverse these ratios, and what we have a over e is equal to q over m, and there we have the expression that we are asked to find. So indeed, we have shown that the acceleration over the electric field is equal to the charge over the mass of the charged particle. All right. So now in question B, the particle has a charge of 4e, where E is the elementary charge. The elementary charge is numerically equal to the charge of an electron and also the charge of a proton, numerically. Yeah? The electric field strength is, okay, it's given, is 3,5 times 10 to the power of 4 volts per meter. The acceleration of the particle is 1,5 times 10 to the power of 12 meters per second squared. All right. Use the expression in A, so this expression, to show that the mass of the particle is 9u. And hold it now, because this is the exam paper, eh? And in the exam paper they do give us the values of the elementary charge, and hold it, where is the beginning of the given goodies? Here it is, in page 2. So we see here we have the where's the elementary charge? Here it is. This is the elementary charge, and the atomic mass unit, the U, is 1,66 times 10 to the power of minus 27 kilograms. It's also given. So this is the atomic mass unit. So these numbers are given. So it's not a problem. So where are we now? What number is that? 5. Here we are. Yeah. All right. So let's write this down. The E, so that we remember. E, the elementary charge is 1,60 times 10 to the power of minus 19 coulomb. And the atomic mass unit, let's write it here, is 1,66 times 10 to the power of minus 27 kilograms. Okay, in SI units. Okay, great. So what is this happening? I use the expression in A to show that the mass of the particle is 9 atomic mass units. Okay, so we're going to work in this formula here. We need to show that the mass is so much. So let us solve this formula for mass. Let's make mass, Q times E, charge times E, divided by the acceleration. Okay. So now we have solved for mass. If we replace here the values, the given values, we should find, well, we should find the mass in kilograms, but then we have to change into atomic mass units. All right. So let us do here, replace the numerical values. The charge, the particle has a charge of 4e. So it's 4 times e, which is the elementary charge, which is 1 times 1,60 times 10 to the power of minus 19 coulomb. I'm not going to write the units. Okay, that would be coulomb, times the electric field strength, which is given 3,5 times 10 to the power of 4 volts per meter, and the acceleration divided by the acceleration, which is 1,5 times 10 to the power of 12 meters per second squared. You see, all these are SI units, and our answer, because it's a mass, we should find kilograms here. And what do we find here? 4 times 1,6 times 3,5 divided by 1,5, all this would give us like 14,9333 times the tens, the powers of 10. Minus 19 plus 4 is minus 15, minus 12 is minus 27, which is nice because we have the same power of 10 as in the atomic mass unit. Of course, the correct way to write actually this answer is actually 1,49 times 10 to the power of minus 26, and that would be kilograms. But it's nice that we found it in powers of minus 10 to the power of minus 27, so that it's comparable with that, and we can get rid of the powers of 10. So anyway, now, so this is the mass of the particle. Now we want to show that this particle is 9 atomic mass units. So in other words, we need to compare it with the atomic mass unit. So, okay. So this mass, which is, I'll take this number here, 14,93 times 10 to the power of minus 27, which is kilograms, divided by the mass of one atomic mass unit, which is 1,66 times 10 to the power of minus 27. You see why I wanted the 10 to the power of minus 27, because now this cancel, which is great, because I only have to divide 14,93 divided by 1,66. And this now, if we do the, we're going to find about roughly very close to the value of 9 atomic mass units. Okay, can correct the significant figures now. So there it is. So we found, I mean, if you do these calculations here, you're going to find 9 atomic mass units, and we show that the mass of this particle is 9 atomic mass units. Here it is. All right. Next, we are told now that the particle is a nucleus, which is a positive particle. State the number of protons and the number of neutrons in the nucleus. Okay. All right, so it's a nucleus, and we know that we found that its mass is 9 atomic mass units, which means all the nucleons put together, protons and neutrons, are 9 altogether. All right, so we have that this nucleus is made out of 9 nucleons, of which some are protons, some are neutrons. Now, how many protons, how many neutrons? Well, already they told us here that the particle has a charge of 4e, 4 times the elementary charge. Obviously, this means that this nucleus is made out of 4 protons. So we know that the number of protons are 4. Obviously, the remaining are the neutrons. So what is the remaining here out of 9? 5 neutrons. So this nucleus is made out of 4 protons and 5 neutrons. So that all together make up 9 nucleons, because we found 9 atomic mass units. All right. So the number of protons is 4 protons, and the number of neutrons is 5 neutrons and protons. Okay. Next, a second nucleus that is an isotope of the nucleus in C. Okay, another isotope is in the same uniform electric field. This uniform electric field. Okay. State and explain whether the electric field produces for the 2 nuclei the same magnitudes of force and next acceleration. Okay. So what? State and explain whether the electric field produces. It means whether the second isotope, which is the isotope of the same type of particle, but which means what is an isotope? It has the same number of protons but different number of neutrons, isn't it? So this particle would have 4 protons as well, but some other number of neutrons. So that would be the isotope, another isotope. Okay. So a second nucleus, which is an isotope of the nucleus in C, is in the same uniform electric field. State and explain whether the electric field produces for the 2 nuclei the same magnitudes of force. Okay, it means that whether the 2 particles, this isotope and the previous one, experience the same force inside the electric field. And the electric field exerts a force in a charge that is found in its vicinity, which is force per unit charge, isn't it? So this force actually depends on the charge of the particle that is inside the field. So if we have a field, a uniform electric field, say, and there's a charge here, Q, this will experience a force which will be Q times E. So the force depends on the charge. So since it depends on the charge, well, now we have nuclei, they are positively charged particles. And what is their charge? Their charge is the same because they have the same number of protons, isn't it? I mean, the neutrons do not contribute to the charge. So they have the same charge, these 2 nuclei of the 2 isotopes. Obviously, they will experience the same force because they're in the same electric field. So the force is the same on both of them. Both of these particles will experience the same force, the electric force. Why? Because, and do we need to explain that? State and explain, yeah. The same force because they have the same, both of those isotopes have the same, because they have the same charge, which is the charge of the 4 protons. Okay, now are they okay, since they both experience a force in the electric field, well, when an object experiences a net force. When a net force is applied on an object, this object accelerates. And we want to figure out now whether the acceleration that these two isotopes will experience is going to be equal or not equal. All right, now, but acceleration now, now we are involving Newton's second law of motion, because Newton's second law says that an object that experiences a net force accelerates. But now in this expression, we have the mass involved. Now the mass of these two isotopes is not the same anymore, because, okay, they do have the same number of protons, but they have different number of neutrons. So they have different atomic mass. Since they have a different mass, obviously, if we solve here for acceleration, the acceleration is force per unit mass here. The force they are going to experience is the same as the electric force, which we said depends on the charge. So this will be the same, but the mass is different now. So the particle with a bigger mass will experience a smaller acceleration, and the vice versa, isn't it? So the acceleration is going to be different now. It's not going to be the same because the mass of the two particles is different. So that is so the answer is the mass is different, therefore the acceleration must be different. So mass is different, therefore the acceleration will be different. It will be different. They will experience a different acceleration. Okay. Is this the end of this problem? Yeah, it's the end of this problem. Okay. All right. So if you have any problems, if you need a question, you can write me a comment. I can see it. I have it in front of me. That's fine. And we can go now to the second problem I would like us to try. Where is this? Yeah, it's another problem from another paper. Which paper is that? From 2017, November, something like that. Okay. Okay. What do we have here? There's the definition. Define electric field strength. As always, always define the electric field strength. So how do we said that it is defined as force per unit of positive charge. They want you to say to include this positive charge instead of saying force per unit charge. Okay, so that the electric field strength is force per positive unit of charge, per positive charge. Okay. Now let us come to the proper problem. So two parallel metal plates in a vacuum are separated by a distance of 15 millimeters as shown in the figure. So this distance is 15 millimeters. They give us here the mass of a particle which is at A, and the charge of this particle which is 1,6. This is equal to the elementary charge probably. Okay, if it's positive, it's a proton perhaps. All right. So a uniform electric field is produced between the plates by applying a potential difference between them. Oh, there is a potential difference, so we know that this is the positive plate and this is the negative plate. Okay. A particle of mass 1,7 times 10 to the power of minus 27 kilograms and a charge of this value is initially at rest at point A on one plate. Here it is. The particle is moved by the electric field to point B on the other plate. The particle reaches point B with a kinetic energy of 2,4 times 10 to the power of minus 16 joules. Calculate the speed of the particle at point B. All right. So this time they give us energy. They link the electric field, the uniform electric field with energy. All right, so calculate the speed of the particle. Okay, well, they give us the kinetic energy here, which is great because kinetic energy is half mv squared, and they give us the mass of the particle. So this is known, it's given 2,4, etc. Find the velocity, all right? So from here, if we solve for the speed, not velocity. What? And we do the calculations. Okay, v squared, that will be E kinetic times these two goes up there, and divide by the mass. And this is 2 times kinetic energy, 2,4 times 10 to the power of minus 16 joules. And the mass, 1,7 times 10 to the power of minus 27 kilograms. And be careful now, this is squared. So, okay, I'm not going to do the calculations. I'm going to find the numbers here. Hold it now. Let me find my things. According to my calculations, this is 28. Or is it 2? I can't figure out my writing. 28. Come on, let me see. Anyway, this is what I see now. I hope I have it right here. Times 10 to the power of 10. This is 10. I can't figure out my letter, my handwriting. So therefore, anyway, if this is a v squared, the v is 5,3 times 10 to the power of 5 meters per second. So here our answer will be 5,3 times 10 to the power of 5. So this is the speed as we find it from the kinetic energy which is given. Remember, this is the kinetic energy of the particle when it arrives at point B, where all its energy is kinetic. Here it starts from rest, all its energy was potential, and because the force of the electric force acts on it, a net force, it will start speeding up from 0, accelerating until it arrives at the opposite side at point B, and then all its energy will be kinetic, and its speed will have this value when it arrives at this negative plate. Okay, now state the work done by the electric field to move the particle from A to B. The next question says state the work done. Well, this is not a big problem now. It's easy because the work done by the electric field was actually to give the particle all this kinetic energy that ended up having on the opposite plate here, this negative plate, that would be the positive. All right, so this work done is actually equal to the kinetic energy of this particle. So therefore we know the work done is 2,4 times 10 to the power of minus 16 joules. So this is the answer here, 2,4 times 10 to the power of minus 16 joules. I'm trying to go fast because the time goes very. All right, so this is the work done. Now the next question says, use your answer into this answer, which is the work, to determine the force on the particle. Well, work done, as we know, the work done is force times distance, isn't it? Distance now is the distance between the two plates, which is given here in the picture. It's 15 millimeters. That's the distance, because the field did work to move the particle from position A to B. So this is the distance that it moved. And the force, of course, this force is the electric force. And this is the force that we need to find. So this is the electric force, really, and this is the distance between the two plates. And the work is this one here. So from there, if we solve for the force, that will be work done divided by distance, and doing the calculation, what's happening here, let me check here. That will be, okay, the work done is 2,4, be careful with the units, times 10 to the minus 16 joules. The distance is millimeters, we have to change it into the millimeters into meters, which means multiply by 10 to the power of minus 3. And we find here, this is 1,6 times 10 to the power of minus 14 newtons. This is the answer that we're supposed to find here, newtons. All right. So quite a straightforward question, this one. Now, next, determine the potential difference between the plates. Yeah, well, now we know the force, the electric force, and we know that the electric field is actually given as force per unit of charge, isn't it? But it's also, particularly in the case where we have a uniform electric field between two parallel plates, like in our problem, the electric field is uniform, meaning it has the same value everywhere. The formula of the field is also given as the potential difference across the two plates divided by the distance between the two plates. So this particular expression applies in the case of a uniform electric field between two parallel plates. So from here, from this part, we can find the potential difference between the plates because I think we have enough information here. If we solve this for potential difference for V, this is F times D divided by Q. And we have all these values. We know the force, we know the distance, we know the charge. And, okay, let me give you the final value immediately. This is 1,500 volts if we replace these values, and we know them all. And this is the answer, the volts. We know the charge, it's given, the charge of this particle. You see, we have the charge of the particle, we have the distance between the two plates, and we found the force. So, all right. So that I'm in a hurry because we need to the last question here. On this figure, sketch a graph to show the variation of the kinetic energy of a particle with a distance from point A along the line AB. So be careful here. This is now kinetic energy. How does the kinetic energy change from the one plate to the opposite plate, up to, from 0, in other words, up to 15 millimeters? And be careful now, this is kinetic energy. And the answer is actually, we should find a straight line, we should show a straight line that stops here at the 15 millimeters, because there is this, where the particle, where is it, where it meets the opposite plate, and then of course it has to stop. But why, we need to understand why this is a straight line. It's because, remember, the kinetic energy, okay, we might be fooled to think because it's mv squared, we think, oh, but it accelerates, starts from 0 and accelerates and goes faster and faster. And we might be fooled to draw a curved line. But remember that this kinetic energy is also equal to the work done by the electric field to move the charge from the positive plate to the negative plate. Remember? So this kinetic energy is also equal to the work done by the field, which is equal to the force times distance. And look at this now. If we look at it in this configuration, we see that the kinetic energy is directly proportional to the distance. So that is why these are directly proportional items, and therefore that is why we get a straight line starting from 0. When it starts from 0 means directly, and it's a straight line means directly proportional. So directly proportional, that is why we get a straight line. All right, so now we have to stop because it's 12 o'clock as usual. And I hope you understand roughly, you have an idea now of how these problems with the electric fields between plates appear and how they combine them with different topics of physics, very often with kinematics, but also with energy, as we saw here. All right, guys. I think next week we're going to start waves, and maybe the Young's double slit experiment, and then the stationary waves. Okay. if you agree. Unless if you have something else to suggest, it will be my pleasure to change topic. All right.